Hello everyone, my name is Randila Beratna and this is my final project presentation for Decision Sciences 726. So what we are doing in this project is to identify a correct number of bikes ready to rent and see how bike rental demand changes according to the weather. We have two goals in this project. The predictive goal of this project is to forecast the demand from bike rental data and forecast the weather from weather data for the next 6 months. The prescriptive goal of this project is using predictive weather forecast and prescribe a more optimal demand value for next month according to the different weather patterns. We forecast the weather just to calculate the prescriptive goal. In real life, they can get the weather information from weather services and apply to our inventory model and get the optimal demand. So Capital BikeShare is a bicycle sharing system or a bike rental company where people can rent bicycle from short amount of time. They have several outlets, therefore people can rent bikes from one place and return it to another place. As we all know, an inventory lower than the demand will lose sales, as well as an inventory more than the demand will add unnecessary inventory cost. If Capital Bike Share can identify the optimal number of bike rentals, then they can lower the cost while increasing the profit. Forecasting bike rental demand from historical data rental is generally not a hard task, but the decision of whether rent a bike or not is highly correlated with the weather of that particular day. And now we'll move on to our data pre-processing part. The dataset was acquired from the machine learning repository in UCI. There are 731 observations and 16 variables in this dataset. Each observation consists data for a single day, and the entire dataset contains data for 2 years. So the main transformation I did was the denormalization of these four variables. In original dataset, these variables were normalized. Even though normalized data is good for predictions, I need the actual value for my prescriptive analysis. Therefore, I denormalize these four variables from their given normalized formula. So this is the distribution of my daily bike rental demand. As we can see here, the number of bike rents changes seasonally. We can see that there is high bike rental count in the summer comparing to the winter. So this is the distribution of our three main weather attributes: temperature, humidity, and wind speed. You can see that the temperature changes throughout the year, but humidity and wind speed does not show any seasonality effect. Here we have all the central tendency measures and dispersion measures. Here we can see the humidity and wind speed has outliers. So therefore, humidity and wind speed, I made a separate dataset without outliers just to see whether these outliers have a large effect on my final outcome. And now let's move on to the data analysis part of this project. First, I wanted to forecast bike demand and weather attributes. To that, I chose time series forecasting. My first time series model is ARIMA. ARIMA, or Regressive Integrated Moving Average, directly models autocorrelation in a series as well as the autocorrelation of the forecast errors. Before apply ARIMA, I remove outliers and use moving average to further smoothen out the dataset. I used k equal 5, k equal 15, and 30 for the moving averages to compare which one is the best. As we can see in this graph, the moving average results with k equal 30, or the blue line is pretty much smoothed out. I divided the dataset into two sets: the first 18 months of data as the training dataset and the last 6 months of data as the test dataset. For a RIMA model, I used Bayesian Information Criterion, or BIC. The first table here shows the best model for each level of moving average according to the BIC. It is very clear that the model with the k equal 30 has the lowest BIC value of 4880. And in the second table, we can see that the higher the k value in moving average, lower the error metric. As we see in this graph, the model did not capture the seasonality component in this dataset. When I tried some functions that are specifically made to seasonal data, I got the error message called non-seasonal data cannot be modeled using a seasonal factor. This made me realize that the seasonal component of this dataset is hard to capture by ARIMA. There are only two yearly seasons and weekly seasonality is not significant enough to the ARIMA model. After the ARIMA, I used the model called time series signature. Time series signature has features that can describe the time series index of a dataset. These features helped us to forecast our dataset. I used R for forecasting and used the libraries tidyquant, timeTK, and Broom. Then I add the time series signature to the test dataset and use the model to predict the values for our test dataset. According to this graph, we can see that the model has predicted the pattern and the curvature of the trend very well, but the predicted values are more compressed compared to actual values. If we draw the residuals for training and test data in the same graph, we can see that model predicts low around June and December while it predicts high around October. After that, I ran the model and forecasted my bike demand value for next 6 months. To calculate the forecast variance, I use the 95% prediction intervals, which shows in the green color. As you can see in this graph, this time series signature model forecasted our data very well. After that, I did the same process to temperature, humidity, and wind speed, and calculated the forecasted value for next 6 months. According to these values, we can see that even though error metrics are a little bit higher than the ARIMA error metrics, we can see the time series signature has captured the seasonality component in the forecasted values. Comparing the error metric values, this approach may not be suitable when patterns are not present or when the future is highly uncertain. But in a dataset like capital BikeShare with a weekly and yearly seasonality, I decided to go with the time series signature model. The next step of this project is to find out how bike rental demand changes according to the temperature, humidity, and wind speed. I chose linear regression model because all these values are numeric values. As for the ratio between training and test data, I chose 80:20. According to this table, we can see that the temperature has a positive correlation with the bike rentals, while the humidity and wind speed has a negative correlation. That means people like to ride on warm days with less wind or probably lower humidity. Comparing the p-values and t-statistic, the temperature is one of the main factors in deciding the demand for bikes. So these three graphs show how the temperature is correlating with the bike rentals and how humidity and wind speed has no significance towards the bike rental. After predicting with the test data, I got some dissatisfying R-squared values. These low R-squared values show that the linear regression does not provide a good model. So, in order to find a better model than the simple linear regression, I tried 8 more models to fit my data. But the maximum R-squared value that I could obtain is 62.94% from multivariate adaptive regression spline or MAS method. Even though the correlation is averagely high, the bike rentals and weather data did not fit extremely well. But for the prescriptive purpose, I used the MAS method or multivariate adaptive regression spline to generate my equation. And now let's move on to the prescriptive analysis. From the time series signature model, I managed to download a forecasted dataset for next 6 months. This dataset includes date, bike rental count, temperature, humidity, and wind speed values. Then I applied multivariate adaptive regression splines or MAS and constructed equations for the regression line. To get this line, I use MAS for bike count versus temperature, bike count versus humidity, bike count versus wind speed, and the bike count versus all these three weather attributes. After all my previous analysis, these are the equations that I created. So this table shows the forecasted values I got from the time series signature model. But remember, the goal here is not to take the forecasted bike rental count, but to calculate the bike rental count according to the weather. Therefore, I used my equations in an Excel sheet and created this inventory simulation model and came up with a bike rental count for different weather conditions. For my calculations, I used the forecasted weather data that I showed in the previous slide. But in the real world, Capital BikeShare can get the actual weather information from weather services and apply those values to these equations. As we can see in the previous table, equation 2 and 3 does not prescribe bike rentals well because these two equations did not capture the seasonality effect of the bike demand. This is true because earlier we found out that there isn't much correlation between humidity, wind speed to the bike rental count. The temperature has an averagely high correlation, but, but the equation 1 is moderately good. But according to our fitted models, taking all three variables into modeling has a high coefficient of determination than considering just the temperature. Therefore, equation 4 is well suited way to identify the future bike rental demand. This dataset is not a large dataset. It has only 2 years worth of daily data. A small dataset with 16 variables could easily cause overfitting. Therefore, I've removed the least significant variables, such as year, month, and hour. I divided the dataset into two different sets. The dataset with first 18 months is my training set and the dataset with last 6 months is my test set. But the time series signature model uses this test dataset to ensure the model does not overfit the data. In a RIMA model, I changed the k-value in moving average to tune my model. I used k equals 5, 15, and 30. I did not do any model tuning to the time series signature because it forecasted the values perfectly. In linear regression, instead of tune one model, I tried 9 different models to get the best result from my dataset. I used one free sampling method, which is k-fold cross-validation, to predict the bike rental demand for the changes in weather attributes. But that tenfold cross-validation model did not give any significant R-squared value. So in this project, I did not find any class imbalance because the dataset majorly consists of time series and numerical data. And now the conclusion. From the two time series models that I have tried, I chose time series signature instead of ARIMA because the ARIMA failed to capture the seasonality in my data. Overall, time series signature model forecasted the data into 6 months perfectly. As for my 9 regression models, multivariate adaptive regression splines or MAS model has the highest R squared of 62.94%. This is not a very significant R square value, but this is the best that I could get from the models that I have tried. Using the mass model, I came up with a regression equation. This equation prescribes the bike rental demand according to the temperature, humidity, and wind speed. I used forecasted weather data from time series forecasting and built an inventory simulation model in Excel. The variation between the forecasted rental demand from the statistical model and the rental demand from inventory simulation is around 35%, but most of our preliminary analysis showed that there is a correlation between bike rentals and weather patterns. Therefore, I recommend using the inventory simulation model to minimize the cost of capital by